Okay, today I'd like to tell you about an award-winning discovery made here on the RPI campus. It is a storage material for graphene, or for hydrogen. So I'm going to start by telling you a little bit about why people like to store hydrogen and use it as a fuel. Also going to tell you about why the current methods fall short and why there is a need for improvement, and what makes the material developed here at RPI so great. So, hydrogen. It is extremely abundant. 70% of the universe is actually in this form, a gaseous form, but it covers a planet in ocean water. It's in the air. It's everywhere. It's extremely easy to produce. You can create it by using electrolysis. You can do it thermally with heat, which is actually part of the reason why firefighters use foam. It's because when they throw water in high temperature fires, it splits into hydrogen and oxygen. So there's an abundance of means to create it. But also it's eco-friendly. Combustion of hydrogen and oxygen produces water and energy. But probably the most attractive thing about hydrogen is its energy content. It has about 3 times the energy per kilogram of gasoline and just under that for methane. So I'd like to tell you a little bit about these. One more thing about why hydrogen is so attractive is because of the huge variety of storage methods: compressed gas, liquefied hydrogen, and hydrides. These are the most popular ones. These are what's being developed right now. So, compressed gas, the first one, stored at about 800 times atmospheric pressure, which is like being at the bottom of the ocean. Has a density of about just under 40 kilograms per cubic meter. Has some benefits. It's technologically simple, very easy to compress gas. People have been doing it for a long time. It's very light. These canisters are, it's gas. And a quick refill time. However, it does have some drawbacks. It takes about 10% of the energy content of the hydrogen just to compress it. It also has a comparatively low storage capacity. So you might remember the chart that I showed. Let's see where it falls on the chart. It's actually this one right here. But the probably biggest drawback about compressed hydrogen, that's right, safety. This is related to the Hindenburg one. I mean, now we have composite tanks to store the stuff, allegedly much safer still. They can crack, they can rupture, they can release the gas extremely flammable. The next method on the list was liquefied hydrogen. Has a density of about just under 80 kilograms per cubic meter, stored at a little under 400 degrees Kelvin. Has some very strong positives. It's technologically simple to liquefy hydrogen. It has a higher density than the hydrogen compressed gas and a quick refill time. However, it does have some drawbacks of its own. The cryogenic system required to store the hydrogen can be quite cumbersome, can be problematic, heavy, and it takes about 30% of the energy content of the hydrogen just to liquefy it. So if we throw liquid hydrogen onto the chart, you see it's this one right here, which is better than compressed gas, but certainly is not the best option. And one other con for liquefied hydrogen, again, that's right, it's the safety issue. Here we have the Challenger disaster, and you can see the solid rocket boosters here, which actually one of them had a flame which caused the hydrogen tank to explode. And this is an issue for cars too, because hydrogen liquid constantly is producing hydrogen gas, which has to be taken care of. So you don't want this as a storage medium for your car. Third option on the list of current methods is hydrides. And the reason why these are interesting is because of this. This would be a schematic of liquid hydrogen. And you can see the molecules they're touching, they're very close. Initially, I did not think that it was possible to get a greater density of hydrogen than this. How is this possible? Well, if you look at these areas right here, the electron clouds, these are actually creating a repulsion between the molecules. So if you could somehow bind up this electrical repulsion energy, you can actually push these molecules closer together. And that's basically what hydrides do. Here we have the hydrogen molecules moving into a hydride structure, into the interstitial octahedral and tetrahedral sites. This is making the electron orbitals actually shrink and become less of a problem for putting molecules together. And you can actually get some pretty good storage densities. This is a simple one-to-one binary compound, which is just like magnesium oxide is one-to-one, so it's something like that. Some of the benefits of hydrides are They're much safer than compressed gas or liquefied hydrogen, and they have the potential to have a much greater storage density. However, room temperature hydrides are not reaching this potential because it requires energy to put the molecules into the structure. They have to overcome an electrostatic repulsion, which normally, for the high density hydrides, requires a lot of heat. So this is a real challenge, which is why you see a low hydrogen density at room temperature here. Also, the systems can be quite heavy. If you can replace an entire gas tank of worth of gas in a car, which is 4 kilograms of hydrogen, get the same travel distance, but with a hydride, that 4 kilograms of hydrogen is going to make the weigh twice as much as the original gas tank. And the recharge times are long, like 24, 48 hours. Probably the biggest drawback about this is where it falls on the chart, right there. Kind of pathetic. It's like 2% density per weight. So this brings us to the topic of my presentation. This is Jawad Rafi. He won the 2010 MIT Lemelson Prize here at RPI. He's holding a vial of his graphene. The actual award he won was for the method to construct it. And graphene is basically one layer of graphite. Graphite being what's in pencils. It's a two-dimensional structure. It has gained some notoriety of late due to its incredible electronic strength characteristics, and now it's going into hydrogen storage. It's an incredible material. So let's look a little bit closer at this material. The actual production method is what won the award. Starting with graphite, you treat it chemically for 96 hours, creating this structure where we've added some functional groups and actually increased the interplanar spacing of this, going from 0.34 nanometers to 0.71 nanometers. We then treat it, anneal it at about 2,000 degrees to give it this sort of jumbled look, which heating again allows a sort of evolution of CO2 gas, which really forces a breakup. Then you heat treat it again to solidify it. You have the material. You can put hydrogen into it, take it out at room temperature with just a little bit of pressure. It's extremely versatile. And here we have a transmission electron micrograph of the material right here. It's most of the time it's like this, but it will be a few layers thick here and there. And they verified the structure with some X-ray diffraction experiments. So some of the pros about the hydrogen: safety, doesn't have the same concerns as hydrogen as compressed or liquefied hydrogen. Room temperature operation, non-toxic because it's carbon, as opposed to some of the more drastic chemicals you find in complex and metal hydrides. Scalable production, the process is simple and we can do it on any scale we would like. And it exceeds the hydrogen storage targets that the Department of Energy set a while back. It's the only material known to do so. In fact, looking into it, I found that cons, I couldn't find any real cons about it. It shows a lot of promise. So in conclusion, we see that graphene offers not only safety, but ease of production and a very high capacity. How high? Well, you remember this chart. I mean, liquid hydrogen, we're looking at just under 80 kilograms per cubic meter, and this is almost twice as much as liquid hydrogen, which is pretty impressive to me. So I think that his award was well earned, and graphene shows promise not just in electronics and strengthening materials, but also hydrogen storage. If anybody has any questions or comments.
That's good. Thank you.